So today I'm going to talk about our short paper, which is an extended abstract discussing initial design and considerations for our system to build to perform model-based novelty adaptation in open world AI. This is joint work with as part of a larger DARPA program, but this portion of it is work with myself, Wiktor Piotrowski, Roni Stern, Shiwali, Mohan, and Johan Kleer. Wiktor and Shiwali are here as well, and so you can engage with them throughout the conference at your leisure. For open world AI, why do we care about this and why is it important? You've certainly heard a number of talks so far on changing worlds or on changing goals earlier today, along with some other talks throughout the conference. And this question of AI systems are definitely outperforming human players in a number of static game domains. So this game over here, which is a variant of Pac-Man, it's in the OpenAI, I think it's in the OpenAI gym. We would all believe that you could train a deep reinforcement learner to outperform humans in this quite quickly. But then once you have small changes in the system, it can lead to the agent making very poor decisions, and the performance being degraded very rapidly. Whereas with people, you can tell them a new rule, you can tell the various changes, and they should be able to still play the game quite well. And so the question is, all right, well, how do we build AI agents that can be designed to rapidly adapt to this type of novel conditions? And I think it's always worth sort of looking at people who have studied exactly how these types of effects occur. So this was out of the UMass Amherst, looking at this exact game and doing a number of things to the game to actually make the game easier to play. So adding a line segment gives you more ways to escape. Removing an enemy also should make the game easier. You have less people you're trying to avoid. Moving the enemy's starting location. And as you can see in the total rewards section, that the agent's performance degrades extremely rapidly for things that should actually improve what you're trying to accomplish. So our approach is what we call hypothesis-guided model revision over multiple aligned representations. And I'll go into a little bit about what that means with a number of examples, but let's focus just on model-based novelty response. So here we're going to have learning allows us to detect novel objects as well as to predict the outcome of actions. We are going to use AI planning techniques because they're a rich way of modeling the world, and we're going to spend some time talking about that over the course of this presentation. And then in model-based theory revision, because you have this composable models of composable component models in AI planning, this allows you to rapidly adapt to a piece of novelty if you're able to identify the cause for why things are not proceeding the way you expect them to. So our system designs has a set of models that uses to interact with the environment. So you're going to have some vision components. You're going to have some components that deal with the mechanics of the domain and how you're going to act on those mechanics. You're going to have some models that deal with other actors in the domain, how you think they're going to be performing. And all of this has to get into questions of the types of actually acting in the world, and therefore you have to deal with quantitative information. And so our general approach is that we want to first be always watching our actions as they're performing and detect when things are not as we expect. And when they are not as we expect, we want to formulate a model for what might allow us to explain that. So in the case here, this is from the Angry Birds game. Maybe you can't see the ice block. And then if you should immediately be able to say, well, this thing might be unstable. And that's a novelty detection we might care about. Once you've characterized that novelty, that actually leads you to this question of novelty response of how do you want to respond, how do you want to act in the world in such a way that will maybe not maximize your performance on this problem, but allow you to improve performance later on. So in this case, we might want to target the empty area to see, is there something there? Our mechanics models should say that maybe there's something there, and therefore we're going to target it and see and try to engage, interact with it in some way. And that gives them an action of which we're going to execute. If we do think that there's something there after we've executed that action, then we can start looking into, okay, let's try to train a new classifier for what that engagement might, what is there an object there that we want to be able to perceive from the environment. Now, I worked in with David Aja and Matt Malino about 8 years ago on different aspects of goal reasoning, interacting with Mike Cox and others. And one thing that comes up again and again is thinking about evaluation in different ways and how you want to think about it. And so this provides a new stance, a new time for us to sort of reflect on this question. And so if we think about the impact of open world novelty, we can see you have some performance over time that's getting better and better as HYDRA is learning about the world. You also have the state-of-the-art systems, which might have been designed or tailored. It might be just a straight line if it's just a hand-authored system with no learning for exactly the best way to perform in a given domain. At some point, novelty will be introduced. The agent doesn't know about this, and you would expect performance to drop off. You would expect the system to perform worse, and then you would expect the system to recover by improving its performance over time. Now, one thing that came up when we were doing the goal reasoning work is that some novelties actually make life better. They actually would change the world, and you actually would be able to, you actually should do better right away, or you should be able to do better. Your asymptotic performance, or the best you could achieve, would be actually better than what you had before. So so there's no way to compare performance scores on the right side of that red line with performance scores on the left side of that red line. The other thing that sort of comes up is comparing the performance of our system versus a system that's designed specifically for that original domain. So that's the state-of-the-art, or SOTA. Presumably, if we are trying to detect novelty and respond to it, we're going to be performing a little bit worse. We're going to be maybe performing slower. We might not be performing, we might not be exploiting all the pieces of information that you would be able to do so on that state-of-the-art system. So we call that the overhead of a system. And the next one is this question of initial novelty impact. So what happens shortly after novelty is introduced? And instead of considering that just the difference in this blue line to the other blue line as that novelty has been introduced, what actually we care about is the comparison between the state-of-the-art that's trained on the pre-novelty problems only. So you have the state-of-the-art system that was designed to work on the left side of the red line, and now is performing on the right side of the red line. What is its performance like? And we want to see what the comparison between that and our blue line system is. You also want to know how the novelty adaptation performs. So how well does it learn from that initial novelty introduction to a later point? And for that, we probably want to compare against a system that was built solely for the novelty that exists in the world. So it doesn't care about the previous problems. We want to see how it compares to the, effectively we're making the overhead statement again, but this time only for the novelty problems on the right-hand side of this line. So in doing so, our approach that we're taking, and that we've argued in the program to take, is that you really need to compare against these baselines that are trained on the pre and post novelty problems. So our approach, the first domain that we're working in is the science birds domain, and we're using PDDL planning to generate solutions to solve these problems. PDDL plus allows us to model the dynamics of the domain using actions, processes, and events. This is extremely important as in science birds, you have limited actions. You can only shoot so many birds. They are continuous in terms of the angle at which you shoot them and the velocity at which you're going to launch them at. And in doing so, there's a sequence of, the continuous processes, which is the ballistic motion of the flying objects of the birds. But you also have these events that occur when you make contact with various objects that will then trigger more processes to exist later. And it's important, some of the agents that play these games of Angry Birds will only target objects that are on the screen that it knows, so it discretizes the space that way. Well, that will clearly avoid, you wouldn't be able to solve the problem on the upper right-hand side there, because you'd have to shoot directly at any of those ice blocks or the pig or the platforms, and you would actually fail to solve the problem in any real way. We have a system that The interface to ScienceBirds provides us with object segmentation. We perform classification of those into a set of known types. And then we're able to write out a PDDL plus model, feed it into a PDDL plus model, PDDL plus planner, UP Murphy. And that gives us a sequence of actions that we're then able to launch back into the game. So that's how those shots above on the previous slide were generated. So one thing you can do with when you start thinking about PDDL plus is that the default model is going to be accurate for those non-novelty levels within some with some approximation. But when you think about novelty introduction, PDDL plus actually provides a way of thinking about domain adjustments that will respond to particular types of novelty. And so this allows you to identify and characterize novelty, as well as the set of moves you would make to change the PDDL plus model to capture things like the increasing the force of gravity, introducing new types of birds, introducing wind, and thinking about changing in the constraints, such as only explosions can kill the pigs. One thing that's interesting in the program is that there's another team that's not allowed to tell us what the actual changes are that they're making in the domain models. And then we get evaluate on problems that we don't see. But they do give us some sample ones. So you saw this problem where we understand the dynamics of how the pigs and birds are interacting with each other, and we can make this really interesting bank shot to get 2 birds with 1 stone. Oh no, wait, 2 pigs with 1 bird. Now, some changes in the domain model. There, all of a sudden, we have a different launch velocity and a different elasticity of collision, it appears. And now when we have, once again, we have a new collision, which now has the bird bouncing way, way, way more than the previous birds were bouncing. So we need to be able to respond to these things and generate the types of, so we need to update our PDDL plus model and then be able to replan and generate solutions to these problems. We treat this as a model-based diagnosis problem. So you have the PDDL plus model and the actions that were performed. You have the observed actions that you saw, and you have the components of the model. At this point, and what we want to do is we want to diagnose identify the faulty component and repair the correct model. So once again, like we are dealing with a continuous space. So we have these 2 trajectories. We have a bird that's observed and a bird that's simulated. By simulated here, we mean that's the bird that we thought was going to happen. That's what our model said was going to happen. And at this point, we focused on the PDDL plus model components of the fluents that are given with the model, and in particular, the numeric fluents. So we give the agent the ability to change those to try to see if they can match the observed and simulated together. And the example that we gave in the paper, that was the case study that we've already implemented and that works in the system, is you give HYDRA the task with solving this basic simple ScienceBirds problem. You have a single pig that you're trying to destroy, and using the default model with the wrong gravity value, your shot overestimates the release angle, and you end up with a missed trajectory. When the diagnosis and repair module then is activated, the inconsistency is identified, and then you're able to launch and hit the pig just the way you would want to. As the reviewers pointed out, and as there's a number of related work, especially from this community. So you have work by Matt Molyneux and that I was a part of, and some folks at SIFT on Discover History, which is a way of using the planning model to update particular discrete fluents. You saw this morning Noah and Hector's work on computing numeric expectations for numeric quantities. And so these ideas are very important for thinking about how do you decide where to localize the various discrepancies you might observe. And you saw Mike Cox discussing his problems with problems. And I think that's, and a big part of that is how do you think about goals in his work? And that's obviously influenced the way that we're addressing this. I think it's also interesting that from this community, you have Dustin Danhauer, who worked on learning the discrete preconditions and effects of the actions, as well as Saif Sadiq's work from yesterday, where you saw how he had a continuous model of the environment. And when he was able to detect changes that took the system outside of a particular mode, he could learn a new mode, which would then correspond to a new set of control parameters. And by doing so, it's much in line with our work of you can have this direct impact, a very quick, rapid learning that we'd like to see, that I think is very important. So before I end, I just want to say one more thing here about why multiple aligned models are important, because everything I showed was just focused on the PDDL plus portion. Well, clearly you don't want to use PDDL plus for object detection and classification. It's also probably not the best language for thinking about opposing strategies or multi-agent systems, all things that would be built into a single system. But if you treat them as individual models you might be able to diagnose and be able to localize problems and predictions to those, then that should be able to allow for rapid learning and adaptation. And thank you all for your time. And we have a long way to go. We're 9 months into a 3.5-year program, or a 1.5-year program. Thank you all very much. And we will talk more at the session immediately following.